Good morning. Hello everybody. Now today's topic is non-homogeneous differential equation of a higher order. First we will see what is a linear differential equation of second order. A second order ordinary differential equation is called linear if it can be written in the form y double dash plus p y dash plus q y is equal to r x, where p, q and r are the functions of x only. If it cannot be put up in this form, then the equations are called non-linear differential equations. Homogeneous differential equations of the second order has a general form axy double dash plus bxy dash plus cxy is equal to rx. This is a non-homogeneous equation, and the associated homogeneous equation is axy double dash bxy dash plus cxy equal to 0. So you are familiar with the homogeneous equations. To obtain the solution of this equation number 2, we have to find out the two solutions. That is, here its general solution to the equation number 2 is given by y is equal to yh plus yp, where yh is the general solution to the associated homogeneous equation and yp is the particular solution to the equation nh, or you can say particular integral. An example of a non-homogeneous linear ordinary differential equation is y double dash plus 25y is equal to e raised to minus x cos x. So here ax, bx, cx and rx, they may be either functions of x or may be constants. But we are going to see here only constant variables, where ax, bx and cx are constants, so differential equations with the constant coefficients. Again we call the definition of general solution, and from there we will see what is the basis. So a general solution of an ordinary differential equation 3 on an open interval I is a solution of the form y is equal to c1y1 plus c2y2. We have already studied all this, and we all know that if the differential equation is of the second order, then we get the two different solutions y1 and y2, and by the principle of superposition we know that its linear combination is again a solution. So here we say that y1 and y2 are the solutions of 3 on I and they are not proportional. c1 and c2 are arbitrary constants. So y1 and y2 are not proportional. It means that they are linearly independent. So the y1 and y2 are called bases of the solutions of 3 on I if they are linearly independent. There are three methods to find particular integral, or you can say particular solution, for the non-homogeneous differential equations. The first one is method of variation of parameters, second is method of inverse operator, and third is method of undetermined coefficient. Today we will see the first method, that is the method of variation of parameters. So here, to solve this equation, replace c1 and c2 with ux and vx in the general homogeneous solution, and we will call it y as yp. We will denote it by yp. That means in the above solution, here y is equal to c1y1 plus c2y2. Here c1 and c2 will be replaced by ux and vx. Differentiating this with respect to x, we get yp dash is equal to u into y1 dash plus v into y2 dash plus u dash into y1 plus v dash into y2. And we will assume that u dash into y1 plus v dash into y2 is equal to 0. That implies yp dash is equal to u into y1 dash plus v into y2 dash. Again differentiating this equation with respect to x, we get the second order differential equation y2 double dash is equal to u dash y1 dash plus v dash y2 dash plus u y1 double dash plus v y2 double dash. Substituting it into, that is, we are substituting all the values u, yp dash and yp double dash in the original non-homogeneous equation, then we get this type of equation. And then rearranging the terms, Finally, we will get u dash y1 dash, we'll get equation number 5. Solving 4 and 5 for u dash and v dash, that is multiplying equation number 4 by y1 dash minus equation number 5 by y1. So on simplifying this, we get v dash is equal to r into y1 upon y2 dash into y1 minus y2 into y1 dash, and we call it this one as w. Likewise, u dash is obtained as minus r y2 upon w. Integrating this v dash and u dash with respect to x, we will get v is equal to integration r y1 upon w and u is equal to r y2 upon w. Substituting this u and v again in the equation number here, that is yp is equal to ux into y1x plus vx into y2x, we will get the required particular integral. Let us see one example. It is a second order differential equation y double dash plus 4y is equal to sec x. Here you can see that the coefficients on the left hand side are constant. So this differential equation is called a differential equation with constant coefficients. First we will divide this solutions into the three major parts. First is to find out the general solution of a homogeneous system. Then we'll have to find out the solution for a non-homogeneous. And the third one is we'll have to add those two solutions to find out the general solution of the non-homogeneous equation. So first step, general solution, homogeneous solution. It is denoted by YH, and homogeneous equation is obtained by taking right side 0. So let y is equal to e raised to lambda x, substitute in 2, that gives lambda square plus 4 equal to 0. This is known as either auxiliary equation or a characteristic equation. If we factorize, we get lambda equals to plus or minus 2i. Hence, y1x is e raised to 2ix, y2x is e raised to minus 2ix. So the complex solution y1x and y2x are given as cos 2x and sin 2x respectively. So here now we can see that cos 2x and sin 2x, they are linearly independent, so they form a basis. Wx is known as the Wronskian. Wronskian is obtained by finding out the value of determinant by putting in the first row y1 and y2 and in second row y1 dash and y2 dash. So by putting these values, we get Wx is equal to 2. For non-homogeneous solution, we know that the solution is given by the term yp is equal to u y1 plus v y2, where u is obtained as integration of r y1 upon w and v is obtained as integration minus r y1 upon w. So let us find out this. Y1 r upon w is equal to 1 by 2 cos 2x into sec x, which gives you the result sin x. Similarly, y2r is half sin 2x into sec x, which gives the result cos x minus half sec x. Hence ux is integration r y2 by w, which gives you the solution sin x minus half log sec x plus tan x, and vx is equal to minus r y1 w, that is its result is cos x. Substituting those values in this equation, ypx is equal to u y1 plus v y2, we get the required particular integral as sin x minus half log sec x plus tan x into cos 2x plus cos x sin 2x. Finally, the general solution is the summation of these previous two solutions. So yx is yhx plus ypx, that is c1 cos 2x plus c2 sin 2x plus cos x sin 2x plus sin x minus half log sec x plus tan x into cos 2x. Method of variation of parameters extension to higher order. So now we will consider a differential equation of order 3. Its general form is y triple dash plus a into y double dash plus b into y dash plus c into y is equal to r of x. Here, as the order of the equation is 3, we will get 3 independent solutions y1, y2 and y3. and all these three independent solutions are linearly independent. So they form bases. We consider the particular integral ypx as ux into y1x plus vx into y2x plus wx into y3x. So now our work is to find out what is ux, vx and wx. For that we are going to do the same procedure as we have done in the previous example. That means I will have to find out yp dash, yp double dash, yp triple dash and substituting all these values in this equation number 6. And solving it, we get u dash is equal to w1 r upon w, v dash is equal to w2 into r upon w, and w dash is equal to w3 r upon w, where w is the Wronskian obtained by the determinant of the bases y1, y2, y3 as a first row, second row y1 dash, y2 dash, y3 dash, and third row y1 double dash, y2 dash, y3 double dash. And w1, w2, w3, that is wi is the determinant obtained from wy1, y2, y3 by replacing ith column by column vector 0, 0, 1. That is, here when I want to find out w1, instead of this first column y1, y1 dash, y1 double dash, I must replace this first column by 0, 0, 1. Rest of the two columns remains as it is, and I will have to find out the determinant value. Similarly, to find out w2, first and third column remains as it is, and second is replaced by 0, 0, 1. And for w3, first two columns remains as it is, third column will be replaced by 0, 0, 1. And u dash, v dash and w dash is integrated to obtain u, v and w, substituting all these values in the yp, which we have considered that yp be the particular integral, that is equation number 7. Hence we get yp, and hence the general solution is obtained as the summation of yh plus yp. So you can solve this, or you can try this example on your own. References is Advanced Engineering Mathematics by Edwin Krasik. Thank you.